Hello everyone, thank you for joining me for today's video. Mr. Ish here. Today might be a long video with a lot of concepts, a lot of things to learn, focusing especially on asymptotes, but generally the video is going to be talking about rational functions. Just right here at the very top line is an example of a polynomial function. A polynomial function looks something like this, where you have a certain degree, a certain order, and it carries down. The exponents carry down up to 0. An example would be 3x cubed plus 2x squared plus x minus 1. That's a polynomial. But here you can see here the letters n. These represent the order of a polynomial. And the order of a polynomial is based on the highest order that you see. If supposedly this was a 3x cubed over here and everything else is a square or to the power of 1 or less, the order of that polynomial is 3 because the 3x cubed happened to be the highest order. So the order will be 3. So keep in mind a polynomial looks something like this. Next we will look at a basic definition of a rational function. Rational function is something like a fraction, except you have a polynomial on the top and a polynomial on the bottom. If f of x represents a rational function, these two aspects here, the numerator and the denominator, can be represented by individual functions, but together as a whole, they combine by means of this fraction line, this divide line, to form a polynomial function. And generally to calculate the domain of a polynomial function, which is in terms of a rational function, is not difficult. You have to keep in mind several assumptions. One assumption you have to keep in mind for sure is when you're calculating a domain of a rational function, are we looking at the rational function in an unsimplified form or in the simplified form? So here's an example of how that assumption, if made or not made, can change your answer. And remember, the domain in general for any polynomial rational function is always, unless otherwise, is always x is an element of all real numbers, except for those numbers where x cannot be, let me make this 2 because we're not speaking specifically about x, we're going to be constrained by this, except in those instances where the denominator polynomial will not end up leading to a 0. See what happens if this entire lower function here, the denominator becomes a 0, this becomes undefined because you'll have something divided by 0 which is not acceptable. So keep in mind that in general, rational functions always have the domain x is an element of real numbers so long as at the lower aspect the denominator does not become 0. But as I was talking about the assumptions, are we going to determine the domain of a rational function in a simplified form or an unsimplified form? I'll show you 2 examples why that assumption matters. If one rational function looks something like this, x minus 1 or x squared minus 1, and we're only going to use this, but we're going to use this in terms of 2 scenarios. If we look at an unsimplified form, that we're making no reduction. Remember in algebra you kind of reduce everything to the lowest terms. If we never made any reduction to the lowest terms and we kept our answer as this, because we know this right here is a binomial which opens up into x minus 1 into x plus 1. Here if you look at it, when we look at the zeros of this polynomial in terms of domain, we know clearly, and you can always refer back to my domain and range videos, that x is an element of all real numbers except x cannot equal to 1 or minus 1. Look over here, the zeros, these, if you make them individually equal to 0, you'll get x is equal to 1 and x is equal to minus 1. So in this, if we never use the simplified version of the same polynomial, here's our domain. But what if we simplified this, as you should in algebra? This was scenario number A. Scenario number B would look like this. In the simplified version, where you're assuming that the domain of the entire rational function should always be in a very simplified form, in that case you would cancel this out because the top and the bottom look alike and you see 1 over x plus 1 as your final answer. Now if you look at the domain over here, x is an element of all real numbers, but now x cannot equal to minus 1. So which of these is the better answer? This one on the top where you've not made the assumption of using the simplest form, or this right here where you have made the assumption that every polynomial rational function should always be in the lowest form? And the answer to that debate is this. You should always make the assumption that rational functions should always be in the most simplified form. So given that as our framework, keep that in mind throughout the rest of this video. Where and whenever possible, whenever you're given a rational function, always try to cancel out what you can. And from the cancelled, finalized, simplified version is where you will determine the domains. Let's look at a few example questions before we actually talk about asymptotes with regards to rational functions where this assumption cannot be made simply because the expression you're given is not simplified further at all. So let's look at some of those cases where an assumption cannot be made to begin with, then we'll continue with the rest of this video. Here is one example where you can do no simplification at all and you have to determine the domain as you see it. See, if you look over here, if you open this up, we should open it up to see if we can simplify them or not. Then we worry about whether we're simplifying or not. If you look at this, there's nothing you can cancel out. So this is one of those instances where the domain is exactly from what you have, this rational function in an unsimplified form. Here the domain will be x is an element of all real numbers, but x cannot equal to 3 or minus 3. So this domain holds true and you didn't even have to simplify this. Here's another example where there's an inability to simplify anything and you just have to continue with what you have. Look at over here, you cannot cancel anything out from the denominator or the numerator. Here again, x is an element of all real numbers, but x cannot equal to 0 because if you put a 0 over here, it will 0 it out and you'll get 1 over 0. Let's look at this one last example before we go to the next topic. Here we have x squared plus 1. In this instance, again, you cannot outrightly simplify or reduce this rational function any further. Therefore, you determine the domain from what you already have. Here it seems like there's absolutely no situation where you can even get a 0 in the denominator. Therefore, your domain is just x is an element of real numbers. There's no exception. And the procedure for determining for sure if there is no exception or not is to calculate the 0. It would be, you'll take that expression and you'll equal it to 0. X squared plus 1 equals 0. Solve for x. X squared is equal to minus 1. And x is equal to square root of plus and minus square root of minus 1. Look over here, we've gotten an imaginary number. Therefore, it all automatically tells you that this curve will never intercept the x-axis because you cannot do imaginary roots. It will never intercept the x-axis, therefore x is an element of all real numbers is our domain over here. So up till now I've talked about the rational function which you know. I'm going to put it right here in the corner, was something which looked like this. F of x was equal to p of x. Remember, p of x, q of x, doesn't matter what letter you're using, but it was something which looked like a fraction, a polynomial on the top divided by a polynomial on the bottom. And we talked about the assumption that if you have any polynomial given to you in a question, always try to factor it out and cancel out as many terms so you can rewrite the polynomial in a condensed, reduced format, the simplest format, or the simplified format from which you determine the domain. Determining the domain is an essential skill because it comes handy when it comes to the asymptotes. And asymptote determination is actually not an easy skill to understand, but it's actually a very valuable skill because you have 3 types of asymptotes in a graph. I'm going to basically just show you the quick gist of everything before we go into the detail. An asymptote can be something which goes in a vertical direction like this. And the asymptote of this vertical direction always has an equation x equals a, where a represents a number which represents the x coordinate where it's going through. And remember, asymptotes are areas where the curve is somehow limited against. It's trying to reach it, but it never reaches it, or it just traverses by it. You can have asymptotes which are horizontal in nature, going from left to right, and these always have the formula y equals b. And remember, a and b here can be positive or minus. I'm just showing everything here in a very generalized manner. You can also have oblique asymptotes, and you know what the word oblique means. Oblique means diagonal. You can have an asymptote which extends in a diagonal manner, and these asymptotes will have some formula y is equal to and some line over here, not just a single letter, but will be an expression. You have to be able to determine from a given rational function with polynomial on the denominator and in the numerator how you can decipher these 3 types of asymptotes by a set of rules. And again, this is a very methodical process where you have to determine these 3 types of asymptotes. Not every rational function will have all these 3, but if you carry out through the series of steps that I will show you, for any given polynomial, you will be able to determine if these types of asymptotes are present and what those asymptotes really are. So just as a very quick example, the type of questions you would be looking at would be something like this. It would be like f of x is equal to some expression on the top. We can just rough house everything over here, divided by 2x minus 1. So if you're given a question which looks like this, you have to be able to look at this type of a rational function and say, is there a vertical asymptote present in here, or how many vertical asymptotes? Are there horizontal asymptotes? Are there any oblique asymptotes? If you can do that just by looking at this and the set of rules I'll show you, and those rules are basically a series of processes you'll follow from like A all the way down to the end. And you can do all of that deciphering, then you're on the right track over here. Before we actually get into this very elaborated process, I should spend some time talking about what a horizontal and vertical asymptote are, because the horizontal and the vertical asymptotes are more important than the oblique asymptotes. So very quickly, we will just talk about those two types of asymptotes in terms of graphing, and then we'll actually proceed with the process of determining all of this. For a vertical asymptote, you can have several scenarios. Again, I'll use this right here, x is equal to a, because vertical asymptotes are always vertical lines, and vertical lines have the formula x equals a. You can have a number of scenarios, and those scenarios are based on how the function is traveling. And there's a specific way of writing this out. If supposedly you have a function which is coming in this direction, and the equation of this function will just be f of x. We're not even getting elaborate here with the equation form. And it's coming up here, and then it shoots up over here. And it shoots up along this vertical asymptote. Remember, it's not going to cross it. It's going to go up and keep traveling along it. Something like this would look in this form. You'll have f of x. And remember, we're always looking at the x value. See the x values here from the minus x to the positive x as, and now you have to learn how to write some notation over here. Remember, we're learning how to write the notation, the limit of x values as you are approaching. Now this is notation we have to learn. As these x values are approaching, what are they approaching? A. What does A represent over here? A coordinate, a comma 0. A is specifically an x value. So limit as x approaches A, and there's a minus sign on this A, like an exponent minus. But that's not an exponent minus, it just means you're approaching this limit from the left. This minus means from the left hand. As this function approaches this vertical asymptote from the left side, what happens to your function? It goes up beyond bounds towards what? Positive infinity. Look at this. I'm going to show you 4 specific scenarios of vertical asymptotes. I'll only show you 2 for horizontal asymptotes. But the special attention here is towards this notation of how you write it. The limit f of x as x values, these x values approach a from the left, this minus sign, what happens to your function? It goes above, beyond the bounds towards positive infinity. Look at this scenario right here. It could be any type of line like this, and then it's coming down this way. How will we write this limit? LIM, limit, as x values. See these x values as they're approaching this a. And they're again approaching a from the left side, so I have a minus sign here. What happens to this f of x? What becomes of it? This right here is what becomes of it. It becomes minus infinity. See, it approaches out of bounds, but towards the minus infinity side. Why is this positive infinity and this minus infinity? Because remember, when you put the input values, you get the output values. The output values are determined based on your y-axis. See, minus y and plus y. If you keep going above a plus, up on plus y, you'll hit positive infinity. Keep going down on minus y, you'll hit minus infinity. Let's look at, I'm going to erase this. Let's look at the same type of asymptote, but we're approaching it from the other side. Look at what happens over here. We have a function which comes over here, then it just shoots down. I'm not going to write over that a comma 0, and it shoots down here. How will we write this? Well, again, it's easy. You write limit as x, these x values along the x-axis approach a, and remember, here's my a, the vertical asymptote a, and the point right over here, which will actually be represented a comma 0. As x approaches a from the right, positive exponent meaning right. What happens to f of x? You can see what happens. It goes down towards minus infinity. Alright, minus infinity. Lastly, let's look at one more type of vertical asymptote description. a function which is coming up in this direction, then it shoots up here. And you can imagine what this will be. Limit as x approaches a from the right, hence the positive sign, the f of x, the function, goes out of bounds but in the direction of positive infinity. You see the curve went up towards positive infinity. So be aware of this. There are 4 ways of showing vertical limits in terms of their notation. 2 of those are from the left hand side, so you'll have a minus sign over here. 2 of those are from the right hand side, so you'll have a positive sign right here. And you always have to be aware of where the x-axis values are approaching. See, x-axis values are approaching a from the right. X-axis values are approaching a but from the left. But what happens to the function? That's the part after the equal sign or the colon. It either goes up to positive infinity or minus infinity. Let me show you a similar schematic for horizontal asymptotes. Then we'll talk about the procedures for determining these asymptotes. So horizontal asymptotes is coming up next. Here's a plot because we're going to be talking very quickly about the horizontal asymptotes. Again, the procedure over here is to learn how do we notate this horizontal asymptote. If supposedly we have a horizontal asymptote over here and we know the equation of this y is equal to b, and we have a certain function. Now look, if you compare this back with the notations for the vertical asymptotes, there's a slight difference, and the difference I will show you. If a function is coming from, let's say, this direction, and it goes above over here and then it keeps going here towards this direction along this, how will we write this? Now this is the slight difference. Look at this. We're still talking about x-axis values because we're looking at a direction from left to right. These are going to be x-axis values. You're not looking at y-axis values until you write the part after the equal sign. This is how you will notate this. Limit as x. Remember in the previous question we were saying as x approaches the vertical asymptote a, but that's no longer the case. Here x is no longer approaching an a. Here x is going and approaching infinity. Look at this, it's approaching infinity. But in which direction are we starting? We're starting from left. We're approaching infinity from the leftward side, so we have to put a minus sign over here. But what happens to the limit of f of x as we move in this direction? What happens to this f of x? It approaches b, because it tries to get as close as possible to this b line. Remember, y equals b. It tries to get as close as possible to this line, but it never reaches it, but it gets as close as possible. So for the horizontal asymptote, as you're approaching your x values towards the direction of positive or minus infinity, your function will always be approaching that asymptote, b in this case. Let's look at one more case of some movement in a different direction. We have a f of x function which is coming and it's going in this direction over here. And remember, these things have to be drawn a little better, not too sloppy, but they're getting close to the asymptote, but they're not going further away from the asymptote. In this example over here, the notation would be this. Limit, again, x is approaching not a, not b, but it's approaching infinity. But it's approaching minus infinity over here. Look at this, it's going in the direction of minus infinity. Okay, as x is approaching minus infinity, but from the right side. What happens to our function, f of x? Where does it approach? It still approaches b. So look at this difference. Here in this side, the function was approaching positive infinity. I didn't put a positive sign over here, but it was approaching positive infinity, and this minus here indicates from the leftward side, but the function approached b. That was your output. Your output value was it became very close possible to b. And on this side, this function over here, limit as x approached minus infinity. This right here is not a minus exponent over here. It should have been slightly here on the side. I just ran out of space because the arrow came in the way. This is minus infinity right here. But the function is approaching from the rightward side, hence a positive over here. Okay, and the f of x in the end approached b. Alright, it approached the y equals b, the b asymptote. Alright, so that's the horizontal notation for asymptotes. You don't have to worry too much about the notation for a oblique asymptote because that just ends up being an equation of a line. Let's look at the procedure involved in how we actually determine the asymptotes of a function. To actually determine how we find the asymptotes, we have to go through a series of 3 steps. Each step may or may not involve a number of other steps. And by me saying 3 steps, I mean each step for the three different types of asymptotes. A step for the vertical, a step for the horizontal, and a step for the oblique asymptotes. Very quickly, before we actually do a procedure, let me put an example over here, because we will use this example to determine a few items which will be necessary for actually seeing what the asymptote may be. And I might change this or make it slightly easier. I just brought this specific example right here because there are a few things you have to see beforehand before we start going over the rules. One is you have to see what n is and what m is. This is just a notation, alright? If we are talking about n, we're just looking at the numerator over here, alright? You could have used any, you could have used a or b, c or d. I'm just using n and m. And when we're talking about m, I will be talking about the denominator. But what exactly is n and m implying? We're talking about here the order. What is the order of the polynomial, the highest exponent you see? What's the highest exponent that you see in the numerator? Because n seemed to apply numerator polynomial and m seemed to apply the denominator polynomial. Well, in the upper polynomial, what's the highest exponent you're seeing? The highest order you're seeing at 3. So in this case, the n value is 3. And over here in the denominator, where m seems to apply that it's based off on this, what's the highest order that you see? I see a 1 over here because everything is always to the power of 1 unless otherwise. So m is equal to 1. So keep this in mind because I may not explicitly mention this again, but you have to decipher this out from the very beginning so you can go through this series of steps. So please keep in mind this terminology n and m and what they entail, because we're going to do a series of tests which will involve the comparison of n and m to determine the asymptotes. So let's bring a easier question and we will look at it in terms of the procedures. And this question will be just a, let's just say a scenario question. If there's a f of x is equal to axn plus, let's say, a over bxm. You see I brought the n and the m plus b. The rule number 1 for vertical asymptote, and I'm going to do abbreviations. Vertical asymptote, I'll do VA. Vertical asymptote. The procedure for determining the vertical asymptote, which we'll follow in the examples that I will show you, will determine the zeros of the function, right? The zeros of your rational function. And we'll also determine the domain, alright? If you can do these two aspects right here, you'll easily determine your vertical asymptote. Remember, it may seem like a lot, but it's actually, all of it is actually very easy. The first step, vertical asymptote, you'll determine the zeros of the function, and you're going to use the zeros of the function always from the denominator, right? From the denominator. And that's what we'll look at, only the denominator for the vertical asymptote. For the horizontal asymptote, what will that entail? It will entail a comparison of n versus m. Alright, we'll do comparison of the n and the m values, and you know from the very beginning you have to determine what your n is and what your m is. I'm just laying you out a format of how you determine this. When we do the actual examples, you'll see it actually make a lot of sense. The horizontal asymptote will be based off on the comparison of n value. Remember, we're like comparing two numbers, alright? Two numbers, and this will lead you to 3 scenarios, alright? Scenario 1, Scenario 2, and Scenario 3. Based on these 3 scenarios, you'll either have a horizontal asymptote, or you may not have a horizontal asymptote, or you'll have a standard horizontal asymptote. Lastly, the oblique asymptote determination will again involve the comparison of n versus m, but in a very specific manner. Here, n must be 1 more than m. What are the n exponent order is? If it's 1 more than m, you'll have an oblique asymptote, right? If supposedly n is 3, m must be at least a 2, because 2 plus 1 will give you a 3, and then we'll determine that. You see, so this is the process how you follow to determine the presence of these 3 asymptotes. You always start with the vertical asymptote, and this right here is the easiest because you already know how to calculate domains, and you always use a denominator and you calculate the zeros of the function. And not every rational function will have all of these 3. Some will have 1, some will have 2. The horizontal asymptote will require the comparison of n and m. And that will lead you through 3 scenarios. Again, easy. Oblique asymptote will require you to compare n and m, but in terms of this. Is the value of n 1 more than the value of m? If it is, then you're good. We'll have an oblique asymptote. If it isn't, then we won't have an oblique asymptote. We may have something which appears to be an oblique asymptote, but you won't have a true one. What you have here before you in a screen, before we actually tackle a specific example, is me trying to explain to you the 3 cases which I alluded to in the very previous segment regarding the horizontal asymptote. Remember I said when we were talking about horizontal asymptotes, is you'll have 3 scenarios which will depend on the comparison of the n and the m values. And I told you when we're talking about this entire video, we're talking about rational functions with the fractional form of polynomials. And again, I also mentioned very earlier on, you have to determine the n and the m values, which are basically the highest order of that specific polynomial. Assuming n being representative of the order of the numerator polynomial and m being representative of the denominator polynomial, you have to make the comparison. And we always look at the highest order. If the value of n happens to be larger than m, this is case number 1 when we're determining horizontal asymptotes, what will happen? It'll basically mean, there is no horizontal asymptote, and I'm using abbreviation HA for abbreviation is horizontal asymptote. If supposedly there is an equality of the n and m values, both numbers are the same, both orders are the same, there will be a horizontal asymptote. We just have to then learn how we calculate it. If there is the order n is being less than the order of m, you will have a horizontal asymptote, but it'll always be your x-axis. In this case, your x-axis is your standard horizontal asymptote, which is always represented by y equals 0. So keep these 3 cases in mind, and you can look them over here before I flip to the next part of this video. N is larger than m, no asymptote in terms of a horizontal asymptote. N is equal to m, there is a horizontal asymptote, and you have to actually determine what that is. Y is equal to something or something, we'll have to determine that. And then n is less than m, here there is a horizontal asymptote, but it actually happens to be your x-axis. In this case, your x-axis horizontal asymptote is always y equals 0. So that's easy. So let me introduce you very quickly in terms of how we will calculate the oblique asymptotes. Remember I said earlier on, oblique asymptotes are something which would look like this, crossing the graph in a diagonal manner. And oblique asymptote is one of those asymptotes we'll determine as step number 3 in our process, which I described earlier. You have to learn how to do polynomial division if you want to determine oblique asymptotes. And remember, the specific rule was the n must be 1 more than m. Remember, n, the order of the numerator polynomial must be 1 more than the order of the denominator polynomial. If that is the case, then you have to do a polynomial division to determine the equation. If you do not know how to do a polynomial long division, you will not be able to calculate the oblique asymptote, which is the equation of that asymptote. As a very quick example, I'm going to show you how we do a polynomial long division, because that will come into play as we determine this specific asymptote. A polynomial long division looks something like this. If supposedly someone presented you a question x cubed plus 2x minus 1, and you have to divide this by x plus 4, and you have to carry this, like a regular long division, but there's a polynomial long division. You have to determine the result of this long division. And you have to learn this skill, because without it you cannot present an answer for an oblique asymptote. The procedure for this is actually easy. You'll write this out as you would a long division, except wherever you have the missing orders you must fill them in, but with zeros. You see I have a cube over here, then I jump to a power of 1, but I'm missing an x square over here. Well, that's fine, I can put a 0x square. Then I can jump back to this next item, which is 2x, then minus 1. And you create your long division, and you do x plus 4. Now you're going to do basically the principles of long division to carry this down to a final answer. Now look how we do this. You always look at the first term. X goes in x cubed how many times? It's simple, it goes x squared times. Now you got to multiply this back. X squared is going to multiply with this x, and then it's going to multiply with the 4, and you put the answers down here. So let's show you. X squared goes in x cubed I should say the x squared times x is x cubed. It's not like going into it, it's actually multiplying with it. X squared times 4 is a plus 4x squared. As always, you put a minus because you want to start cancelling out terms. When you put a minus, this thing cancels out, the x cubes cancel out, but then you get a 0x squared minus 4x squared, and that gives you a minus 4x squared. You bring the next item down, you have a 2x, a plus 2x because you have a plus over here. Now you see x goes, remember you're always using the first term, x goes in minus 4x squared how many times? It goes minus 4x times, right? Minus 4x times x will give you minus 4x squared. Now you take this term and you multiply it twice with the first term and the second term and you put them directly underneath. Minus 4x times that x is a minus 4x squared. Minus 4x times this 4 is a minus 16x. As always, you do a minus sign because this minus sign, depending on what you have, to cancel out the first term, these ones will cancel out. You will get a 2x minus minus 16x, I'll give you an 18x. Alright? Lastly, bring this minus 1 down over here, and this will be our last item over here of this solution. X will go in 18x how many times? It will go positive 18 times. Multiply this 18 back with these two items. 18 times x is an 18x. 18 times 4. Let me bring out my calculator. 18 times 4. I get a 72, but it's a plus 72. Put a minus sign to cancel out these first terms. You get a minus 1, minus 72, you get a minus 73. Last step is to actually write our answer in a proper format. The answer in the proper format is this. You're going to write what you have here on the top because that actually is your answer. Then you'll write a remainder if there is. My answer is this. X squared minus 4x plus 18. You see, x squared minus 4x plus 18. And put a plus sign because the remainder adds to all of this. See, our remainder here is a minus 73. It's a minus 73 over this item right here, which is your denominator item. X plus 4. So if you divide this polynomial, assuming I've not made any mistake over here, this right here is my answer. Okay, this part plus the remainder part. The remainder minus 73 out of what you were using as your divisor. So for the oblique asymptote, you have to know this procedure. Why? Because this right here will be your equation of the oblique asymptote. This right here will be your equation for oblique asymptote. But again, remember I told you specifically before that the value of n must be 1 more than the value of 1. But look over here. In the rational polynomial, my value of n was actually a 3. Here my value of n was 3. But here my value of m was a 1. It's not 1 more than the value. N is not 1 more than the value of m. It's actually 2 more than the value m. And as I alluded earlier, then this means it's not a true asymptote. It's not a true oblique asymptote. It's something which will give you the appearance. This equation will be an appearance of what an oblique asymptote will be, but it's not your true oblique asymptote. Why? Because the value of n exceeded the value of m by not 1, but by 2 units. See, the 2 units, cube and a 1, that was a 2 unit. Here, n was equal to m plus 2, right? So this right here spoils your ability to get a true oblique asymptote. But regardless of this rule having been succeeded or failed, it doesn't matter. You still have to learn the procedure of calculating of polynomial long division. But if you have a question which looks like this, you can automatically say, because the n is equal to m plus 1 rule is not being followed, right? You can always just say there's no true oblique asymptote, and you can eliminate the whole procedure for finding out a true oblique asymptote. If you have the procedure where if you have the scenario where n is actually equal to m plus 1, then you must carry out this process and determine the equation for that oblique asymptote. I think it would be most reasonable now to actually show you specific examples where we will play out all the 3 asymptotes for each of those examples. So that'll be what we will be going through next. Again, the best procedure for determining the process by which we actually calculate the 3 asymptotes, the vertical, horizontal, and the oblique, is by doing specific examples. And as you know, I started this with the discussion of rational functions, but the main aim was, whenever you're given a rational function, something with a polynomial on the top and 1 in the bottom, numerator and denominator, our goal for this video was actually to determine the 3 asymptotes. So without even having to use a graphing tool, you should be able to pluck these 3 asymptotes if they exist from any equation. So that's a real goal of this video. We're going to start first for this specific example in this order. We'll always try to determine the vertical asymptote, then we'll see if there's a horizontal asymptote, and then we'll see if there's an oblique asymptote. And the procedure we'll follow specifically will be this. For vertical asymptote, I'm going to always look at the denominator. When I look at the denominator, I'm going to try to determine the 0. 0 is actually your x-intercept, right? Or x-intercept or root. If you were to solve for that expression algebraically, you're solving for x. So I think the better answer, the better term is always to determine the 0 of that expression. And this is how we'll do it. You'll do x minus 2, and I'm looking at the denominator, is equal to 0. X is equal to 2. Why are we determining the 0 of this expression? Because the 0 of this expression is what will make the denominator 0. And we know here our denominator, if you put a 2 in place of x over here, the denominator will get zeroed out. And as I told you, for vertical asymptote, you want to express a domain. X is an element of all real numbers, but x is not equal to 2 because that's a 0. But whatever your exception ends up being is actually your vertical asymptote. All you have to do is write the vertical asymptote in a proper equation. And that equation for vertical asymptote is always x is equal to a. What was my a value is what my 0 value was. So my vertical asymptote for this expression, this rational function, is x is equal to 2. So the vertical asymptote has been completed. So we're done with that one step. Our next goal is now for the horizontal asymptotes. The horizontal asymptote requires you to determine the n and the m values first. Remember, n is the highest order of exponent of your polynomial in the numerator, and m is that for the denominator. What's the highest order I'm seeing in the numerator? I see 2x to the power of 1. So my highest order for n is 1. But look here in the denominator, it's also x to the power of 1. So my highest order in the denominator is 1. And I showed you the 3 cases where you compare for a horizontal asymptote. Is n greater than m? Is n equal to m? Or n is less than m? In each of those specific scenarios, you have a specific outcome. Here n is equal to m. N is equal to m. Therefore, there is a horizontal asymptote, and we have to determine that. The procedure for doing that is actually easy. It's a process you will see a lot when you're learning limits for calculus. You take your numerator and you divide it by the highest order item you have in terms of your variable. What's the highest order item I have over here is an x to the power of 1. I divide whatever I have on the top by my highest order variable, which is an x. You do the exact same for your denominator. I have an x over here, highest order meaning an exponent of 1. I'll divide everything over here I see by x. And then you carry it out. What do I end up with on the top? 2x divided by x is a 2. X minus 2 divided by x, I'm going to separate them out, is a 1 minus 2 over x. I separated them out. X divided by x is a 1. 2 divided by x is a 2 over x. So 1 minus 2 over x. All you have to do is now take the limit of x. Extend it all the way up to infinity. If you make this number so large, as you know, when you divide a small number by something really large, you start getting to 0.0000, meaning this whole thing zeroes out. Because if you take this limit of x so large, you'll end up with such a small insignificant number here that it will have no bearing on this 1. So eventually you will end up with something which is just 2 over 1. And this right here will be your horizontal asymptote. The horizontal asymptote over here will always be in the form y equals b. But here my horizontal asymptote is y is equal to 2. Here's my horizontal asymptote. Using this specific procedure, why? Because n was equal to m. Oblique asymptote, last step. For oblique asymptote, you always have to see, is n equal to m plus 1? Is the order of n 1 more than the order of 1? The order of m. But look over here, I'm seeing n is equal to m. It by no means can satisfy this equation. So therefore, there is no oblique asymptote in this question. You just have a vertical asymptote, which happened to be an x equals 2, and you had a horizontal asymptote, which happened to be y equals 2. Graphically, I'm not going to graph the curves, but I'm going to show you the asymptote. X equals 2 would have been this right here, your vertical asymptote. Your y equals 2 would have been your this asymptote over here. If you were to make like a rough graph over here, I would picture the curve would be something like this. going close to this horizontal asymptote, both sides going close, but coming up to this vertical asymptote, separated, not a continuous but a discontinuous function, affected by a vertical and a horizontal asymptote. So you see here, we calculated a vertical, a horizontal, and there was no need to determine an oblique asymptote. But you can see it's a procedure, it's a process. Start from the way top and work on the way bottom. You have several tests that come into play, and those tests will determine if those asymptotes exist or not. So let's keep doing some more examples. Let's look at this rational function. 2x squared divided by x minus 2. There's nothing wrong with you determining the n and the m values from the start. N value, the highest order exponent that you see in the numerator. I see a 2 because it's an x squared. I'll just put n is equal to 2. M, the highest order exponent that you see in the denominator, which will characterize the order of that polynomial. Remember, a polynomial can be a single term, it can be 2 terms, it can be 3, 4, 5, however many terms. But at the end of the day, they're all polynomials. M value for the lower is an x to the power of 1, which is a 1. Let's determine the vertical asymptote. Vertical asymptote, as you know, you're calculating the zeros of that function, right? Procedure for that is take your expression in the denominator, make it equal to 0, and solve for x. X minus 2 equals 0, x is equal to 2. So we know here our domain is x is an element of all real numbers, but x cannot be equal to 2, because if it were equal to 2, you'd get a 0 in the denominator. But what x was not equal to is actually a vertical asymptote. Therefore, my vertical asymptote here happened to be x equals 2, because vertical asymptotes are always x equals a lines. Vertical asymptote is done. Yes, it's a process and a procedure, but it's easy. Our next process is to determine is horizontal asymptote. I told you specifically 3 scenarios exist when you compare n versus m. If n is larger than m, you have no horizontal asymptote. If n is equal to m, you have a horizontal asymptote which you have to calculate. We did that in the previous example. If n is less than m, you have a specific horizontal asymptote which always ends up being your x-axis, y equals 0. But here, my n is larger than m. See, for the horizontal asymptote, my n is larger than m, therefore no horizontal asymptote. But that's fine, there is no horizontal asymptote, we're done. We don't have a horizontal asymptote. But by no means can you say against the fact that for this type of function, the function will always proceed towards the direction of positive or minus infinity as your x values go from positive to minus infinity, right? As you make your x values exponentially large, your function will probably go in the direction of infinity. As you make your x values infinitely small towards minus infinity, your function will very likely also proceed in some direction of that infinity. So just because you have no horizontal asymptote doesn't mean you don't have a horizontal direction, right? You may have a horizontal stretch going towards infinity. Lastly, oblique asymptote. Is there an oblique asymptote over here or not? What's the procedure for that? N must equal to m plus 1. If n is something larger than m plus 1, you can still determine an oblique asymptote, but it will not be a true oblique asymptote. For a true oblique asymptote, n must always be m plus 1. Is n equal to m plus 1? Yes, it is, because if you take this m and add 1 to it, you get 2. And the only way, without knowing this rule, is to look over here. If the order on the top is always 1 more than the order on the bottom, you will have an oblique asymptote. Look here, we have an x squared, we have x to the 1. It is definitely 1 more on the top. And as I showed you, for an oblique asymptote, you must do polynomial long division, because the result of that polynomial long division will give you the equation of that oblique asymptote. We have an x minus 2 which is being divided into 2x squared. But look over here, I don't have any further terms over here, but that's fine, I'll add them out. And by further terms, I mean adding them out so that this exponent zeroes out or it dies away. I'll put a 0x and I'll put a 0. X goes in 2x squared how many times? It goes 2x times. Then you have to remultiply this. 2x times x is 2x squared. 2x times minus 2 is a minus 4x. Minus them out, because you're always minusing them out to get rid of the first term. You do a 0x minus 4x is the same thing as just a 4x. X goes in 4x how many times? I'm going to just bring the 0 down for completeness. This x goes in 4x how many times? It goes plus 4 times. Remember this equation I get here on the top, this answer on the top will be my equation. 4 times x is a 4x. 4 times minus 2 is a minus 8. Minus them out so you can zero out the first terms. You get a 0 minus minus 8, you get an 8. I'm going to write this answer here in a proper format, and I showed you that. The answer on the top of this divide line right here is my answer with a plus and added by with the remainder. Remainder here was 8 over what you started with right here, x minus 2. 8 over x minus 2. So the equation of my oblique asymptote is y is equal to 2x plus 4. Here's my equation of the oblique asymptote, which is right over here. So as your function goes infinitely in one direction, your curve will start getting closer to the equation of a line 2x plus 4, but it's not a true line, it's an asymptote line. So in this example we had a vertical asymptote. We did not have a horizontal asymptote, but we did have a oblique asymptote. And if you were to graph something like this, let's do a very quick graph. Let's draw our vertical asymptote. Vertical asymptote was x equals 2, right here, x equals 2. Let's draw an asymptote for 2x plus 4. It's a steep line moved up by 4 units. Steep line moved up by 4 units. It'll probably be something like this. And we're going to be proceeding beyond the confines of this graph. We'll have a situation where we'll have one curve like this and another curve right here on the top within the confines of this asymptote. You see this? I know I've kind of ran into my other numbers, but you can see how the asymptotes affected the shape of that curve. So this was another example where we had the presence of some asymptotes. We had 2. Let's look at another example. Let's look at this example. F of x is equal to 2 divided by x minus 2 whole square. Again, a rational function. I'm going to start this time a little slightly different. I'm going to determine the n and the m values first. Remember, n is the highest order of the numerator, m is the highest order of the polynomial on the denominator. What's my n value over here? If I have an x over here, it must be to the power of 0, because that power x to the power of 0 kind of removed that whole x. See, x to the power of 0 is equal to 1, so here n is equal to 0. What about my m value? And I'm going to erase this just for the purpose of staying neat. When you have something like this in a block, in a parentheses with a square, you could imagine if you had opened up this parentheses x minus 2 times x minus 2, you would have ended up with an x square, meaning the highest order of that denominator, the m here would have been a 2. Now let's look over here. This is a test for an oblique asymptote. Is n equal to m plus 1? It isn't, because n is actually 0. So you know in this case right here we will have no oblique asymptote. So that's easy. We may have a vertical asymptote, we may have a horizontal asymptote, but definitely there's no oblique asymptote. So what at the very beginning of this video seemed like it might be too much work, actually in most instances is not. Because if you can do some of these tests very early on, you can eliminate some of the work right away. Our first step, in my opinion, should always be the determination of a vertical asymptote. And the vertical asymptote, as you know, is the determination of the zeros. It's easy. Take your denominator expression and make it equal to 0, because you're determining the zeros over here. Take the exponent on the other side, 0, root is 0. You get x minus 2 equals 0. Take 2 on the other side, x is equal to 2. So we write the domain over here. X over here is always element of all real numbers, because all real numbers will solve this, except for that one specific number or 2, which will lead to a denominator of 0. And that specific number is your 0. Which you calculated, which happens to be a 0, which happens to be a 2. But whatever your 0 happen to be is what your vertical asymptote is. This right here is your vertical asymptote in the proper format. X equals 2. That's your vertical asymptote. If you put 2 over here, you'll get a 0, and you get a denominator of 0. The next and last step is to compare your n and m values to determine your horizontal asymptote. And I showed you earlier there are 3 scenarios. N is larger than m, if n is equal to m, or if n is less than m. Which situation do we fall into? N is 0, m is 2. We fall into this situation where n is less than m. And I also told you in this situation, you'll always have one specific asymptote, and no matter what type of question it is, the asymptote will always be your x-axis, and the equation of x-axis is y equals 0. See, your x-axis is a horizontal line, y equals b, but going through the origin with an x value of 0, 0. Hence, x-axis horizontal lines are y equals 0. So here we've determined our horizontal asymptote, here we've determined our vertical asymptote, here we show that there is no oblique asymptote, and the question is done. Easy question. Graphically, not drawn to scale, let's draw a vertical asymptote. X equals 2. I'm just putting it aside from here so it doesn't hit and interfere with that. Horizontal asymptote, y equals 0. This right here is my horizontal asymptote. Graph would look something like this. Okay, and you can think back to the beginning of this lesson where I was talking about how you would write this in terms of limit. Limit as x approaches 2. The vertical asymptote part, limit as x approaches your a value, which is 2. Remember 2, 0, 2. The function f of x exceeds above all bounds in a positive infinity direction. And here we're approaching 2 from the left. And I'm talking about vertical asymptote over here. Look at this, limit as x approaches again 2, but we're approaching it from a rightward direction, 2. Your f of x, your function, will again exceed above all bounds, but again in a positive infinity direction. Those are your vertical asymptotes explained, right? Graphed in proper notation. Here is another rational function. Remember again, in terms of asymptotes, generally most rational functions will usually have two asymptotes, either a vertical or horizontal, and very likely if there's a horizontal asymptote, you'll very likely not have an oblique asymptote. In this specific example, f of x is equal to x cubed over x squared plus 1. I will start again with this process over here. N, m, and n is equal to m plus 1. What's my n value? It should be second nature by now. Always look at the highest order of the polynomial in the numerator. I see a 3. Remember, the highest order is representative of your exponent that you're looking at. M over here is a 2. This is a 2 over here. X squared plus 1. Is n equal to m plus 1? Is 3 equal to 2 plus 1? Yes. So therefore we will have an oblique asymptote. We will have to calculate that at the end. The first step, as always, in my opinion, should be the determination of a vertical asymptote. And you'll be pleasantly surprised that in this question we will not have a horizontal asymptote. Vertical asymptote. Calculate the zeros of the equation. X squared plus 1 equals 0. Now I'm looking here at the denominator expression. X squared plus 1 equals 0. Take minus 1 on the take 1 on the other side to make it a minus 1 is equal to minus 1, and then x is equal to square root positive minus of root minus 1. Look at this, we're getting an imaginary number over here. So this tells you clearly that there will be no vertical asymptote. So there's no vertical asymptote over here because we cannot determine the zeros of this. So that's good, one less item we have to deal with. This might be one of those examples where we'll have no vertical, no horizontal, but we will have an oblique asymptote. For the horizontal asymptote, think back to the comparison of n versus m. If n happened to be larger than m, there was no horizontal asymptote. N was 3, m was 2, there was no horizontal asymptote. But it by no means negated the fact that your function can proceed in the direction of positive or minus infinity as you make the values of x approach positive or minus infinity. Meaning if your values of x are going beyond the extremes in either direction, your function will also go beyond the extremes in either direction. So this factor that there is no horizontal asymptote does not affect this condition of this expression. This expression will continue towards positive and minus infinity. Lastly, and in the interest of showing you the oblique asymptote, I need to create some space because I have to do the polynomial long division. I will erase this part over here, the vertical and horizontal asymptotes, because we've established there are no vertical and horizontal asymptotes. And let's do the long division. Long division process is easy. You write the denominator comes out, the numerator goes in. But look at this, I have missing terms over here. I need to see those missing terms because it makes it easier mentally to actually solve them out. And I always start from the highest exponent to No, x1 and see x cubed, x squared, x1 and x to the power of 0. And we will just sequentially solve this using always the first term. X squared goes in x cubed how many times? It goes a single x time. Then you got to take this and multiply with the two items. X multiplied by that x squared is an x cubed. That same x multiplied with this 1 is an x. Always minus because it will cancel out those terms. You have a 0x squared minus x. Well, 0x squared is meaningless. I just end up with a minus x. Can x squared go into minus x? It cannot. So your polynomial long division is actually finished. You have to just write this in the proper format. The item you get here on the top is actually your main answer right here. Then you always put a plus sign because that plus sign is where you're adding your remainder. What's your remainder here? It's a minus x. It's nothing wrong with putting a plus and then a minus x here or here. What's your part you're going to put underneath this line? It'll be what this term was. X squared plus 1. This right here is your oblique asymptote. The equation of the oblique asymptote will be y is equal to x. So as this function proceeds in the direction of positive or minus infinity, your rational function will become ever closer to this y equals x. This actually will be our last example. I purposely wanted to add this as an example because up till now I may have neglected in this entire video to mention the fact. Remember at the very beginning I talked about that assumption that when we're talking about rational functions with terms with regards to their domain, we want to try to simplify the function to the maximum extent possible, then work with that finalized or the simplified expression to do the determination, especially of the domain. Well, in all the examples I gave you, we were never able to simplify those examples to begin with. So that assumption never came through again in this video. So this again will be another one of those examples where we cannot simplify, we proceed with what we are given because nothing from the top will cancel out. Even in terms of isolation, we cannot simplify this further. And that has been basically the main types of examples I've presented. Unsimplifiable expressions, polynomial rational functions. So in this question, x squared plus x equals this divided by x squared minus 3x plus 2. I want to start by this process because this is how I like to do it. You can always do however you want to do it, but this is how I will do it. Again, the maximum n value I see in the numerator is a 2 because that represents the order of the polynomial on the top. X squared plus x has an order of 2, so therefore n is equal to 2. M, looking at the denominator, x squared minus 3x plus 2, I see an order of 2, m is equal to 2. Oblique asymptote test. If n is equal to m plus 1, there is an oblique asymptote. Here n is not equal to m plus 1, but rather n is equal to m. So we have no oblique asymptote. So it will save us the process of the polynomial long division, which is fine. The first thing I'm going to look at again is the vertical asymptote, and I will do that always by calculating the zeros. Alright, it's like a zeros. You can think of this as like a slang term, but calculating the zeros. For that, you look at the denominator. You will try to factor it out and solve for the values of x by making the expression equal to 0. I see this is factorable as x minus 2 times x minus 1 is equal to 0. Because if you condense it back, if you multiply it back, you'll get that. And I see x is equal to 2 comma 1, because if you separate these and make them individually equal to 0, x is equal to 2 and x is equal to 1. Domain, x is an element of all real numbers, but x is not equal to 2 and 1 because these are vertical asymptotes. At x equals 2 and x equals 1, we'll zero out the denominator, we'll end up with an undefined polynomial expression. So what's my actual vertical asymptotes? They are x equals 2 and x equals 1. Two vertical asymptotes. Fine, you can have multiple. Lastly, horizontal asymptote. What's the test for that? You compare n and m. If n is larger than m, there is no horizontal asymptote. If n is equal to m, there is one, and we have to specifically determine it. If n is less than m, there is always a horizontal asymptote, but that is always y equals 0. Here n is equal to m, so we have to determine that specific asymptote. And the procedure for that is always to simplify your polynomials using a technique that you will learn when you start calculus, by using the highest order item and dividing everything by that same order. I see, looking at the numerator only, I see an x squared. I'll take the entire numerator and I'll divide that by x squared. I'll look at the denominator next. I'll see the highest order here is an x squared, and I'll divide everything by that x squared. This is a technique you will learn when you're studying limits. And look what happens when I do all of that. When I simplify this individually and I'm looking at the numerator, I'll get x squared divided by x squared, which is a 1. Plus, see this plus, and I'm separating these out. X divided by x squared, I get a 1 over x. I'll show you why I'm doing this, and I showed you this in a previous example. X squared divided by x, looking at the denominator, I get a 1. Minus 3x divided by x squared, I get a 3 over x. Plus 2 over x squared. Alright, that's cool. So what do we do with all of this? You assume limit as x approaches limit. As x approaches to infinity, what will happen to these x's? If I make x infinitely large, you'll have 1 divided by an extremely large number. Imagine if you're dividing 1 by 1, you get a 1. But if you make x infinitely large, you make this entire part right over here infinitely small. Think about it. 1 divided by million, 1 divided by a billion, 1 divided by trillion is extremely small. It's so small that if you add that very small part onto this one, it's negligible. So when you do this limit, you're essentially living with only that 1 on the top, because this thing right here is zeroed out because it became too small. And the same thing over here, 3 divided by something very large is too close to 0 that you can cross it out. 2 divided by infinity square is again so small you can cross it out. You're left with what? 1 over 1, which is what? 1. And this right here is your horizontal asymptote. My horizontal asymptote is always in the form y equals b. See, y equals b. But b is this value you determine right here. My horizontal asymptote is y equals 1. So you'll have a plot. You'll have 2 vertical lines, one at x equals 1, one at x equals 2, and a line, horizontal line at y equals 1. I'm not actually drawing the plot, but I'll show you the asymptotes. Here's my plot. I'll have my x equals 2 over here, x equals 1 over here. These are my vertical asymptotes. Y equals 1 will be somewhere over here. And this function will be split into 3 curves. There'll be one down here, or maybe one up here, one in between these two, and one on the other side. So it'll be a single function split into 3 parts by these asymptotes. And this is what you will look like, what you will look at as your final answer. But you'll use a graphing tool to actually plot the curves. So that's how you determine the horizontal, vertical, and oblique asymptotes if they exist. I know this was a difficult and long video, but it's not very hard. If you look at how I broke things down in a methodical manner, if you follow it in the same series of steps, n, m, and then the test, and then the vertical, horizontal, and oblique, and the polynomial long division, it rather becomes an easy topic. Do a lot of these examples and the whole procedure will become second nature to you. Feel free to look at this video several times. It might help you to do so. Please like, share, leave comments, and subscribe. Thank you for watching this video. Have a great day. Bye.